Welcome, everyone. Today we're diving into the fascinating world of waves. You might not always notice them, but waves are everywhere. They're how we hear music, how we see light, how we stay connected through cell phones and Wi-Fi, and even how we understand distant stars through telescopes. They're the invisible threads that weave energy across our world, sometimes through matter, sometimes through space itself. In this lesson, we'll explore two main categories of waves, mechanical and electromagnetic, and examine what they're made of, how they move, and what makes them different. You'll also learn about the essential properties of waves, wavelength, frequency, amplitude, and speed. These are more than just vocabulary words. They're tools to help you understand energy transfer and systems all around you. So let's get started by asking a deceptively simple question. What exactly is a wave? When we talk about waves in science, we're not just talking about ocean waves or the wave you do at a football game, though those are great examples. In physical science, a wave is defined as a repeating disturbance that travels through space or matter and transforms energy from one place to another. That's the key idea. Waves move energy, not matter. Think about shooting a rope or dropping a pebble into a still pond. That up and down motion causes ripples to spread outward. What you're seeing isn't the water itself traveling across the pond. It's the energy moving through the water. The water molecules mostly stay in the same area, just moving up and down. This is true for sound waves, light waves, and even the electromagnetic waves that carry signals to your phone. Waves are all around you, and they make modern life possible. Yet we rarely stop to think about what they actually are. So now that we've got a working definition, let's look more closely at the different kinds of waves and how they behave. To really understand waves, we first need to understand oscillation. Oscillation is just a fancy word for a back and forth motion that repeats over time. Picture a swing at a playground or a pendulum ticking back and forth. These are examples of oscillating objects. They move away from a central point, then return and repeat the cycle over and over. That central point is called the equilibrium position. It's the point where the system would rest if there were no disturbances, like the center of the swing's arc or the resting point of a pendulum. In a wave, particles or fields oscillate around this equilibrium, and the disturbance caused by the motion travels outward. So while the object or particle may move up and down or back and forth, the energy that causes the motion is what propagates as a wave. This idea, repetitive motion around a balanced point, is the foundation of every wave we'll study, from sound and water waves to light and radio waves. Waves come in two major types, mechanical waves and electromagnetic waves. The key difference between them is whether or not they need a medium, that is, a substance like air, water, or solid material that they need to travel through. Mechanical waves, like sound or ocean waves, need matter to move. The energy is passed along by particles bumping into each other. For example, when someone talks, their vocal cords create vibrations that move air particles, which then carry the sound to your ears. Without air or some other medium, sound couldn't travel. That's why in the vacuum of space, no one can hear you scream. Electromagnetic waves, on the other hand, are completely different. They don't need a medium. They can travel through the vacuum of space. Light from the sun reaches Earth this way, traveling over 90 million miles through empty space. These waves are made of oscillating electric and magnetic fields working together to move energy. So whether it's visible light, radio waves, X-rays, or microwaves, they're all electromagnetic, and they don't need matter to carry their energy. Mechanical waves need something to move through, a medium. because they move by making particles in that medium vibrate. Think of a stadium wave. One person stands up and sits down, causing the person next to them to do the same, and the wave travels around the stadium. No one person runs around the seats. The motion passes through the group. That's how mechanical waves work. They pass energy along through particle-to-particle interactions. Sound is a perfect example. When a drum is struck, the drum head vibrates, pushing air molecules. Those molecules push the ones next to them, and so on, carrying the sound to your ears. But if there were no air, like in a vacuum, there would be no particles to pass the vibrations along, and you wouldn't hear anything. That's why mechanical waves, such as sound, water waves, or seismic waves, cannot travel through space or a vacuum. They need matter to carry their energy. Unlike mechanical waves, electromagnetic waves do not need a medium to travel through. They can travel through the vacuum of space. That's why we can see sunlight even though there's no air between Earth and the sun. The waves are made up of two oscillating fields, an electric field and a magnetic field, which work together to carry energy. They don't need particles to bump into each other the way sound does. Electromagnetic waves come in many forms: radio waves, microwaves, infrared, visible light, ultraviolet, X-rays, and gamma rays. This group makes up the electromagnetic spectrum. Whether using a cell phone, heating food in a microwave, getting an X-ray, or just walking in sunlight, you're interacting with electromagnetic waves. Their ability to move through both matter and empty space is what makes them essential to everything from communication and medicine to astronomy and photography. Now that we understand what waves are and how they move, let's look at the two main ways waves can travel: transverse and longitudinal. These terms describe the direction that the particles in the medium move compared to the direction the wave is traveling. In a transverse wave, the particles move perpendicular, or at a right angle, to the direction the wave travels. Imagine shaking one end of a rope up and down. The wave moves forward, but the rope moves up and down. Light waves and water surface waves are good examples of transverse waves. In a longitudinal wave, the particles move parallel to the direction the wave is traveling. A great example is sound. If you push a slinky back and forth, you'll see areas where the coils bunch together and spread out. That back and forth motion is what carries sound to your ears. So while both types of waves move energy, they do so in different directions, something that affects how they interact with matter. Let's take a closer look at transverse waves. In these waves, the particles of the medium move up and down while the wave itself moves forward. The motion is perpendicular. That is, it's at a 90-degree angle to the direction the energy is traveling. A great example is the wave traveling along a rope. If you shake one end of the rope up and down, the wave moves horizontally across the rope while the rope itself moves vertically. We also see transverse waves in electromagnetic waves like visible light, X-rays, and radio waves. Even though those waves aren't moving through a physical medium, they still follow the same perpendicular motion, just with electric and magnetic fields instead of particles. Another familiar example is waves on the surface of water. The water stays mostly in place, but moves up and down as the energy passes through. This distinctive motion helps us recognize transverse waves when we observe them in nature or in technology. Now let's turn to longitudinal waves, which behave quite differently from transverse waves. In a longitudinal wave, the particles of the medium move back and forth in the same direction as the wave is traveling. Instead of going up and down, the motion happens parallel to the wave's path. The best example is a sound wave. When you speak, Your vocal cords create vibrations that push air molecules together, a compression, and then pull them apart, a rarefaction. These compressions and rarefactions move outward from the source and carry the sound to someone's ear. Imagine a slinky stretched out on a table. If you push and pull one end, you'll see tight areas, compressions, move along the coils. That's exactly how energy travels in a longitudinal wave. Just like transverse waves, longitudinal waves move energy, not matter, from one place to another. One of the most important things to understand about waves is this. Waves carry energy, but they do not carry matter. That means the waves move through the medium, but the particles in that medium don't travel along with the waves. They just oscillate around their original position. Think about a buoy in the ocean. When waves pass, the buoy bobs up and down, but it doesn't drift away with the wave. The water is moving energy forward, but not pushing the buoy along. This is true for all kinds of waves, sound, light, even seismic waves during an earthquake. The energy travels through the medium, causing local vibrations or oscillations, but the medium itself stays mostly in place. This is how waves can transport energy over long distances without needing to move an actual material from point A to point B. Now that we understand how waves move energy, let's break down the shape of a transverse wave. Two of the most important features to recognize are the crest and the trough. The crest is the highest point of the wave, where the medium is displaced the most upward from its resting or equilibrium position. The trough is the lowest point, where the medium is displaced the most downward. These 2 points help us visualize how the energy of the wave is moving through the medium. The greater the distance between the crest or trough and the equilibrium line, the more energy the wave is carrying. In just a moment, we'll use this foundation to understand other properties like amplitude, wavelength, and frequency. But for now, just remember, crest is the top, trough is the bottom, and they show us the wave's vertical motion. Amplitude tells us how much energy a wave is carrying. In a transverse wave, amplitude is the vertical distance from the equilibrium line to the crest or to the trough. They're the same height either way. The bigger that distance, the more energy the wave is transporting. For example, a loud sound wave has a larger amplitude than a quiet one because it's pushing air particles farther from the resting position. A bright light wave has a greater amplitude than a dim one because it delivers more energy to your eyes. In a longitudinal wave, like a sound wave, amplitude refers to how tightly the particles are compressed in a compression zone. So whether it's sound, light, or water, amplitude helps us measure the wave's intensity. That is how strong or powerful it is. Wavelength is the distance a wave travels before it starts to repeat itself. In a transverse wave, that's the horizontal distance from one crest to the next crest, or from one trough to the next trough. You can also measure wavelength between any two identical points in a wave cycle, as long as you're measuring from one point to the next point where the pattern starts again. Wavelength is important because it helps us understand how energy is spaced out in a wave. Longer wavelengths usually carry lower energy waves, like radio waves. Shorter wavelengths, like X-rays and ultraviolet light, carry more energy. In longitudinal waves, like sound, wavelength is measured from the start of one compression to the start of the next. So whether the wave moves up and down or back and forth, wavelength helps define the rhythm and spacing of how that energy travels. Frequency tells us how often a wave occurs in a given period of time. More specifically, it's the number of complete wave cycles from crest to crest or compression to compression that pass a point every second. We measure frequency in hertz, where 1 hertz means 1 wave per second. You can think of frequency like checking your phone. If you check it 60 times in an hour, that's a high frequency. The same goes for waves. Higher frequency means more waves packed into a shorter time, and usually a shorter wavelength. For example, a high-pitched sound has a high frequency, while a deep bass note has a low frequency, and light blue has a higher frequency than red. So frequency helps us understand how quickly a wave is delivering its energy, and it's a key to understanding both sound and light. The period is the time it takes for one full wave cycle to pass a given point. If frequency tells us how often waves occur, the period tells us how long each wave takes. The two are closely related. If you know the frequency, you can calculate the period using the formula T equals 1 divided by F, where T is the period in seconds and F is the frequency in hertz. For example, if a wave has a frequency of 2 hertz, that means 2 waves pass by every second. So each wave takes half a second to pass. Its period is 0.5 seconds. Period is especially useful when we want to track the motion of individual particles in a wave. In a sound wave, it tells us how quickly the air molecules are vibrating. In a light wave, it tells us how fast the electric and magnetic fields are oscillating. So while frequency and period measure different things, they always work together to describe the rhythm of a wave. Now that we've talked about wavelength and frequency, we can combine them to understand wave speed. How fast a wave travels through a medium. The formula is simple. The wave speed equals the frequency times the wavelength, or V equals F times lambda. This tells us that a wave speed depends on how frequently it cycles and how far each cycle travels. For example, if a wave has a frequency of 10 hertz and a wavelength of 2 meters, it travels at 20 meters per second. Wave speed depends on the medium. Sound moves faster in solids than in air, and light travels faster in a vacuum. But once you know the frequency and the wavelength, you can figure out how fast that wave is moving. This relationship helps scientists and engineers in everything from designing communication systems to studying earthquakes and ocean currents. Now that we've covered the key properties of waves, amplitude, frequency, wavelength, and speed, it's time to see them in action. One of the best ways to visualize how these properties interact is by using a simulation. Simulations are powerful tools that let us visualize scientific concepts in ways we can't easily observe in the real world. In this scene, we'll preview the PhET Physics Wave on a String simulation, an interactive tool that allows you to explore how waves behave when different properties are changed. Using this simulation, we can send waves down a string and adjust key variables like amplitude, frequency, and damping. You can even change the tension of the string to see how waves reflect off fixed or loose ends. As you experiment, pay close attention to how the wave's shape, speed, and energy change depending on the settings. Try increasing the frequency. And what happens to the wavelength? Observe how a larger amplitude affects the wave's energy. Watch how waves bounce back when they hit different boundaries. This hands-on tool helps bring abstract wave concepts to life, allowing you to test, predict, and understand wave motion in a dynamic and engaging way. By now, you've learned that waves aren't just abstract scientific ideas. They are deeply connected to the world you live in. Waves power much of modern life. You hear your favorite music because of sound waves. You stream videos and make phone calls thanks to radio and micro electromagnetic waves. Doctors use x-rays to see inside your body and ultrasound waves to monitor a baby's heartbeat. Even the heat you feel from the sun is delivered by infrared waves. Understanding how waves work helps you make sense of how technology, communication, and even nature function. Whether you are studying earthquakes, building better Wi-Fi networks, exploring space, or learning how light behaves in photography, the physics of waves is behind it all. This isn't just testable knowledge, it's a framework for understanding the hidden patterns that shape our universe. Before we wrap up, let's take a moment to review the big ideas we've explored. First, we learned that waves are repeating disturbances that transfer energy, not matter. They come in two major forms: mechanical waves, which need a medium like air or water to travel through, and electromagnetic waves, which can even move through the vacuum of space. Then we explored two types of wave motion: transverse waves, where oscillation is perpendicular to motion, and longitudinal waves, where it's parallel. We also broke down the key properties of waves: amplitude, which is the energy; wavelength, the distance between cycles; frequency, how often cycles occur; period, how long each cycle takes; and speed, how fast the wave travels, using the formula V equals F times lambda. Understanding these properties not only helps you explain how waves behave, but also gives you insight into the invisible energy systems all around you. Keep these ideas in mind. They'll keep showing up throughout the physical sciences. Thanks for being part of today's exploration of waves. As you've seen, waves are more than a science lesson. They're a lens for understanding the world. Whether you're watching sunlight filter through clouds, feeling the vibrations of a favorite song, or using your phone to connect across the globe, you are experiencing the power of waves in action. I encourage you to keep asking questions and exploring these patterns in the world around you. The more you understand wave behavior, the better prepared you are to think like a scientist, observing, modeling, and applying knowledge to real-world problems. This is just the beginning. From physics to chemistry to earth science, the ideas we explored today are foundational. Stay curious, keep learning, and remember, science is a wave worth riding.